Hey, this is Brock Lemires, and in this video I'm going to introduce the inductor. Okay, so let's begin by looking at kind of the theory of operation of an inductor. So we've kind of talked about, Faraday's law of induction, and we've seen this phenomena happen that when you run current through a coil of wires, it actually will create a magnetic field. So you can create a magnet. It's actually called an electromagnet. But what we're concerned about when we talk about inductance is the properties of that coil of wire itself. So what does it look like if we just treated it in terms of the two terminals that we see right here? So an inductor can be thought of as a coil of wires. I mean, and in most cases, it really is a coil of wires. And what we care about is what is the size of the magnetic field that we create? And we call that the magnetic flux. So all these lines right here, when you sit there and you talk about, a coil of wires, it's going to create this magnetic flux. And the more current you put through it, you can imagine the more, you're going to have all these lines right here. And we call that the magnetic flux, and we give it this symbol like this, where the B stands for B field, and then this symbol right here is phi, so uppercase phi, this little fella right here. And so you can just think about it as like how strong these fields are matters, right? It's like, because that's what we care about. And so we call this the magnetic flux, which is like a measure of like how many field lines are actually in there. And so what inductance is a measure of how much magnetic flux you get when you run current through that coil of wires, okay? And it is a two-terminal passive device. So it is an energy storage device, and you say, well, how is it storing energy? Well, it has to do with this. When you run current through it, all these magnetic fields are produced, and then if you then cut off the terminals, this magnetic field wouldn't vanish instantly. What would happen is it would slowly go away, and so that means that the current would actually continue to flow through this thing. So we say that an inductor stores electrical energy as a magnetic field or as magnetic flux, and that leads you into some of the behavior of an inductor, which namely, you can't change the current through it instantaneously. Okay, so inductance is the ratio of how much magnetic flux you get per current, and it has a unit of Henry after a scientist. And now this is where it gets a little interesting. I think this is probably the concept right here that makes most people confused about inductors when you first learn about it. You can either try to understand this or you can just forget about it and just remember the math. But due to Faraday's law of induction, there's kind of like this back and forth happening where you run current through the coil, you get magnetic flux, okay? But then if you have any change in the magnetic flux with respect to time, if this varies at all, then what you get is that induces a voltage. Okay, so this is like Faraday's law of induction. One of the things that he came up with was this whole relationship between the magnetic flux and the voltage. Now, once again, all of this is AC. None of this works at DC. Okay, this is all AC. And so what we say is that 1 Henry worth of inductance actually generates 1 volt per 1 amp. But it's an interesting thing because it's actually, the voltage is related back to the force that you can feel, right? So it's an electromagnetic force equivalent to the energy of 1 volt. Okay, so that's really where it gets kind of interesting. Because remember, Faraday was looking at all this stuff of how magnetic fields and electricity and force all interacted. So when you look at his laws, it's trying to always combine kind of everything. Okay, but anyway, really what you care about is this. Okay, and then we'll come back to this in a second. Construction. Most inductors, most large inductors, really are coils of wires. Okay, so you see, if you break open your motherboard, if you have a big inductor, it's going to be a coil of wires. You can actually make the magnetic field stronger, so you can increase the flux if you put something inside of it. So sometimes you have a coil of wires with just air in it. That's called an air coil. Not very strong, but you can put stuff inside of it like iron, okay, or ferrite, and you can increase the magnetic flux. And so a lot of times you see the coil wrapped around stuff. Here's another example. You can get small ones, okay? So you can get ones like this, but a lot of times they're either coils of wires wrapped inside of this. But then there's another type of material. They've found material that acts like an inductor, and it's a ferrite material. And this is how you get like the really small inductors that you might see like on a printed circuit board, like for microelectronics. Okay, so let's get back to describing the behavior of an inductor, because what we really care about is always the current and voltage relationship. So the symbol for an inductor is this. Okay, so you can draw it like that, or you can draw it like this, and it is. That's it. Okay, and it reflects that it's a coil of wires. Don't be. This one is kind of dangerous right there, because it looks like if you do a sloppy resistor, it's like, what's the difference between that and that? So you can't really tell. So I always say, do the coil of wires. That way everybody understands that it's a coil of wires, okay? Okay, so here we go. The characteristics of the voltage to current are described by a differential equation, similar to a capacitor. But let's take a look at that. If I start with L is the ratio of the magnetic flux that I get per 1 amp of current, and I rearrange this, I can move I over here. Okay, so I move I over there, and now this is where you got to keep straight, because this is phi sub lowercase or subscript b. That's the magnetic flux. This is current. Okay, and I have my magnetic flux over here. Well, we kind of knew from before that if I just take the derivative of the magnetic flux with respect to time, that is voltage. So if I come in here, I can say I want to take the derivative of the magnetic flux with respect to time. Well, you got to do it to both sides of the equation, right? Well, then you come over here. Inductance is a constant. It is a property of the material, but I varies with time. So you got to get the old derivative of that buddy in there. So I'm going to do that. And what you're left with is this. This now becomes voltage, and you can rewrite the equation for the voltage across an inductance as simply L multiplied by the derivative of the current with respect to time. And that is now the governing equation of an inductor. Okay? And it's like, oh, that's awesome. All right, so now let's take a look at how that leads to behavior of the inductor, okay? When we talk about the current and the voltage, there's actually a phase difference between them, just like there was in a capacitor. And let's take a look at why that is. So let's do our test case again. In this situation, if I had a current that was flowing through the inductor, okay, so I had like this current that was coming in here, and it was I of t with respect to t, and it happened to be given, just let's do our sine wave. So let's do a sine, and then we had 2 pi f t. So that's the current expression, and I run it through this equation. What I'm going to have is I'll have v of L is equal to the inductance multiplied by di dt. So I'm going to take the derivative of sine 2 pi f t and all of that with respect to time. Well, remember, the derivative of the sine is a cosine, but then you also have to take the derivative of the inside, which ends up just being that constant. So what I'm left with is L multiplied by 2 pi f, no t, that's the variable, times cosine of 2 pi f t. Okay, so immediately you see, and it's like, oh, my voltage is, if my current started as a sine, my voltage ended up with a cosine. Now it is scaled, absolutely, but let's just plot it out and see what kind of phase relationship we get. So if I started with this now as a sine wave that describes my current through the inductor, okay, then I come along and I have my voltage as the cosine right here, and so this right here is my v of t, and I can look at that and go, okay, who's ahead and who's behind? Well, we say that there's a 90-degree phase shift, so 90-degree phase shift, and remember that is, I use 90 degrees with respect to a 360-degree cycle, and I can say that the voltage is leading the current. Okay, so I say that the voltage leads the current in an inductor. Okay, and another way to write that down is you could say, you remember this acronym right here, ELI. Okay, so you got E, which is electric field. That's the physicists use E. We use V, but VLI doesn't really rhyme. So we go ELI. The voltage leads the current in an inductor by 90 degrees always. Okay, so now this is where you can remember this, Eli the ice man, Eli the Iceman. And that's just a reminder of that, how the voltage and current lead or lag each other in inductors and capacitors. And you just remember the letter in the middle is either it's a capacitor or an inductor, and then E and I, this is voltage, that's current, and you can always tell who's in front and who's behind. When you say a voltage leads the current, you could also say the current, what we say, lags the voltage, okay? But whoever is first, okay? All right, so life is good. So that's the phase shift behavior of an inductor. Now let's take a look at kind of when you look at the voltage and current with respect to how fast they can change. Number one, if you look at this equation, right? You look at this equation right here, VL equals L di dt, just the property of an inductor, okay? So it's a coil of wires that creates a magnetic field, and then when you pull away that if you stop driving it, the magnetic field doesn't go away, and it induces a current that continues to go. So the current cannot change instantaneously. The current cannot change instantaneously through an inductor, okay? However, the voltage can. So in this circuit, let's say for an example that I applied a step voltage, okay? So this was, let's say this is T equals 0, and this was Vs right here, okay, Vs of T. And that's what I hit across the inductor. And let's just say that, there was no current flowing in this to begin with. What would happen if I plotted the voltage and the current is this. If I plotted the current through the inductor, it couldn't change, but it would ramp up to something. Okay, so it ramps up, and that would be the current through the inductor with respect to time. Cannot change instantaneously. Okay, but notice that it has this nice exponential ramp. So it's going to have this nice exponential ramp, which is basically given by this time constant thing, which you'll learn about when you take circuits. But it does have this characteristic exponential ramp. And then if you took the voltage away, like if it came over here and did that thing, then the current would basically exponentially decay. Okay? So very, very awesome. All right, can the voltage change instantaneously? And the answer is absolutely. So the voltage can just shoot up, right? It could just instantaneously go up. But then it will then decay back down, also following this exponential decay. So what we say is that the current cannot change instantaneously across a capacitor, but the voltage can. Notice in this circuit that when you first hit it, the inductor, you look at this and you go like, what is this going to look like at DC? Okay, so this now leads us into what it looks like, whether it's AC or DC, and we start thinking about it in terms of, a sine wave sweep. Okay, so let's now sweep a sine wave across it. And we come up with kind of this similar expression for an inductor in terms of like at DC it looks like something, and at high frequency it looks like something, just like with a capacitor. But let's consider this for a second. Let me do a plot versus frequency. That's not frequency, frequency, okay? And what I want to do is I want to start with like 0, and then like 1, and then like 10, and then like 100, and then like 1,000. And these are, this is hertz, okay? And what that means when I draw a plot like that is I'm essentially going to put in a really, like DC is going to be a flat line. Then I'm going to put in a really slow sine wave for that, and then it's going to be like a faster sine wave, then a really fast sine wave, then a really, really, really fast sine wave. And I'm interested in what these look like, okay? All right, so to begin with, let's start with DC. Okay, so this is DC. If I think about DC, can current flow through this wire? And it's like, absolutely, right? It's just flowing because it's a coil of wire. It's conductive. If you ohm this out, it would look like a short, okay? And in fact, that's what it does look like. So at DC, an inductor looks like a short. So in this circuit, I would actually have this, okay? I'd actually have a short circuit right there, and this would be my voltage, okay? That would be the inductor. So when you look at something like that, it's like, okay, so you have a short circuit, no voltage can develop across it, okay? Because it's a short, right? It's like resistance is 0, so V equals IR, you can't get a voltage. And so what happens is, even though you're saying there's a component there, and I look at the voltage across that, it's 0. So what happens is that at DC, it is a short, and in this circuit, okay, only in this circuit, it doesn't develop a voltage. So then what happens is that as you go faster and faster and faster, if you think about this VL is equal to L di dt, what you're doing is you are making the current oscillate back and forth faster and faster in this thing, and the voltage will start developing more and more because you're starting to induce these magnetic fields in there, okay? And so it's like, oh, this is great. And so in this circuit, as you get higher and higher and higher in frequency, what'll happen is that over here, if you draw the circuit, you will have an inductor that looks like an open circuit, Okay, and so it will allow all the voltage to be induced across it because of these magnetic fields. And so that's why we say that at DC it looks like a short, and at high frequency an inductor looks like an open. And so for this circuit, if you think about that, all the voltage from the source right here would be developed across the inductor. And that's because your rate of change of current going back and forth is so high that it's like, oh my gosh, this thing is just crazy. You could let all the voltage in the world and develop across this, meaning that it looks like an open circuit. And so that's kind of the model that we use. So in this circuit, if you had an open circuit, Vs would be VL. And so if I come back up to this plot and you kind of plot this thing right here, so this is the most voltage we have in the circuit, you would actually have something where it kind of like over time the thing goes up, and at some point you would have all the voltage developed. Okay, and so this is kind of the frequency domain behavior of an inductor when it's an RL circuit. And you notice something, this is like a filter. Okay, so this is now a filter that essentially blocks lower frequencies from getting out, and then it allows higher frequencies to go through. So this is called a high pass filter. Okay, and that's essentially it. Now, you know what's really cool about this? Not to talk about capacitors, but check this out. Remember this little buddy? Remember our RC circuit? Remember what the behavior of that was? That was a low pass filter. Okay, so that was a low pass filter where it allowed lower frequencies to go and it blocked higher frequencies. So you can see right now, just with inductors and capacitors, you can build a high pass filter, a low pass filter, or you could essentially let certain ones go through and build a band pass filter. So you can build all sorts of really cool stuff with inductors. Okay, so that is it. That is the inductor. So the big thing to remember about it is an energy storage device, but it stores the energy in the form of magnetic fields, and its IV characteristics are governed by a differential equation. All right, that's it, and see ya.